Okay. Gonna go over first what we did in the MDE 61. Okay. And what we did there is first ask everybody to construct the basic toolkit exponential shape. Okay, I can't see that it's over there on that board. And all screens. And we're developing this. It got interrupted by the computer. No way I could stop it. Decided to reboot. It was managed by VHCC. I love our IT people. They're great. And I sent them an urgent email. It gave me like 12 minutes notice. So I didn't quite get, I don't know exactly where I got cut off. So I'll go through all this. Now, quickly, you recall the two sketch the basic toolkit shape in this class, at least. And if you're in the MDE 61 and not in my class, you can ignore this, okay? This is unique to my class, as far as I know. I'm not explaining this as I go, I'm just doing it so everybody is supposed to master this about 100 years ago. And if you haven't, we need to go back and do that. But there's what the graph looks like, okay? Now I sketched same graph over here, didn't do a very good job of it. You know, it's supposed to go halfway from here to here. So I go halfway from here to here, I get here. And then halfway from here to here is here. And, you know, I didn't quite get halfway when I did this. Maybe did a fairly good job of halfway here, and little fuzzy here. And then when I divided it in the middle, I divided it a little bit too far to the left. And as a result, especially this last interval between here and here, between these construction lines, between this one and the right edge, got too wide. Okay, so they're going to be, well, we're not going to expect great estimates here. Okay. Now, when I did that, I did something we haven't done before. I said, remember the y equals 60 times 1.05 to the t function that we looked at last time. Okay. That's an exponential function. There's some terminology that goes around this that I'll go over in a few minutes, but if I want this graph to represent this function, well, I'm not going to do this in a 4x4 rectangle. I just do it in any old rectangle that is going to fit my needs. And then knowing that this doubles in about 14, okay, okay. The 5 is 5%. The 1.05 is what we multiply a number by to increase it by 5%. If we interpret this as the value of an investment, where T is time in years, and you're getting 5% compounded annually, that's what this represents. Okay, and that's what this graph will represent if we use the right doubling time. Now we can calculate the doubling time, but we haven't yet been over the technique for doing that. We will here shortly. But on the graph, notice that, you know, this graph doubles since each of these lines is twice as close to the lower edge as the one before it. Then if we go up, each line is twice as far from the lower edge. And since the y values are on those lines, every y value doubles. Okay? Each y value doubles because of the way we construct it. Now, you know, and you do pre-calculus, you do it with numbers, but nobody understands the numbers. Well, some people do, but very few people have any clue about negative exponents when they come into our pre-calculus classes. And you know, this is due to the fact that everybody can put themselves in any class they want to, regardless of whether they know what they're doing or not. Now, most of you that are still in the course have demonstrated that you know what you're doing. Okay, you have a decent algebra background. And people who are no longer here for various reasons, you know, life interferes sometimes, and background has its effect on people. I would say out of the 20 odd people who registered for this course, not over half a dozen really had the algebra background to do successfully. Okay. Another half dozen with extremely hard work and consistent homework, which we didn't see that much of among most of our students. Anyhow, point is, I started with this construction because anybody can do it. You don't have to understand negative exponents. You don't have to have a good algebra background. Anybody can do this. Okay. And if you do it, you understand right away why these values double every time you move over this far. Okay. There's this thing called the rule of 72 or rule of 70 or whatever, rule of whatever, which kind of depends what rule you use, kind of depends on what your percent is, but it works. And that rule tells us that this should double about every 14 years. If you just divide 5 into 72, you get 14.4. So actually, that's about 14. Okay. And that's a handy rule. It's a handy thing to know. You'll see it in your open math assignments. Okay, but we then say, well, since this thing doubles every time you move over one of these construction lines, then these construction lines must be 14 years apart. If it's doubling every 14 years. Now, that's not exact. It's fairly close. It's close enough to make some good estimates and get lucky and have the estimates come out better than they deserve to be based on questionable graph that I construct. Okay. All right. Now, so each of these intervals is going to be 14 years, and we understand because of the way this thing's constructed that these things double. Also because this is a graph of the 2 to the x function. Every time x increases by 1, 2 to the x doubles. Okay, but algebraically understanding that is very challenging. So we're going with a picture, and then we'll put the algebra around the picture. All right. So I declared that this now represents this function where t equals 0 right here. And I said, okay, imagine that this is an investment. Okay, that a company been in business for a century, made more than 28 years ago, then t equals -14 and t equals -28 could make perfect sense if t equals 0 is today. Okay, so we say t equals 0 is today, and today y equals 60. Now, see, I didn't even hit y equals 60 very well there. Okay, again, it's because I wasn't as precise as I would like to be in marking my points, and especially because of the distortion over here. Okay, that's not relevant. This is still going to give us some pretty good results. So we want to understand that when t equals 0, 1.05 to 0 is 1, and that gives us y equals 60. Okay, so here's t equals 0, and here's y equals 60. We should have gone through this point. Well, we're close enough. We'll live with a little bit of discrepancy because we're going to learn to do the algebra and everything. Okay. So then 14 years later, what's T? Well, it's 14. And 14 years after that, what's T? Well, it's 28. Okay, these are 14-year increments on our construction line. 14 years ago, T was negative 14. Negative 14 means 14 years ago. T equals negative 28 means 28 years ago. That's how we understand this graph. Now, if y equals 60 on this construction line, what does it equal on this construction line? Well, this construction line is twice as far from the lower edge as this one. Really isn't the way I drew it. I drew that one too high, but y is 120 there then. Okay. And then this construction line is twice as close to the lower edge as this top edge. So on the top edge, the value is going to be double the 120, which is 240. So we're getting a scale on this thing. We don't start with a scale. We construct the graph and then we put the scale on it. There's a lot to be learned by doing that. Now, sometimes, we have a scale. Sometimes we even have graph paper, which I despise. If you want to get really accurate stuff, you use graph paper. Okay, if you want to understand what you're doing, you construct your own plane graph with your own construction lines. Okay? You don't have somebody give you a piece of graph paper and tell you to plug in numbers that you don't understand into a calculator. Okay? Again, reason we have approached the course this way. Okay? So all those numbers, the y equals 60 here, the y equals 120 here, the y equals 240. Just follow from the way we set this up. Okay. Now, we want the value at t equals 10. Okay. That means the value of our investment. What's the value of our investment? Well, is t the value? Yes or no? Now you're shaking your head. That's all right. That's as good as a thumbs down. Okay. No, t is time in years. What is the value? Well, it's y. Y represents the value of this investment. Incidentally, this could also be the population of a herd out in the wild, where they have favorable conditions so that they can continue to grow exponentially. Okay. Maybe it's a herd of whales out on the prairie. No, whales don't live on the prairie. But anyhow, a herd of some kind of an animal whose population, given favorable conditions, doubles every 14 years. Okay? Maybe it's even the population of a human tribe or whatever that has, in the distant past, has inhabited a new valley that nobody knew about, and their population doubles every 14 years. Okay. In this case, though, we'll talk about money doubling every 14 years, roughly every 14 years, at 5% per year. Okay. We're increasing at 5% every year. Whatever our population is, it increases by 5% every year, so that it doubles about every 14 years. Okay, we want to make sense of all that today with the algebra and everything else. So on the graph, t equals 10. What's t equals 10? On the graph, it's a vertical line at 10 because, this vertical line is t equals 0. This construction line, this vertical construction line is t equals 14. T would be 0 here, t is 14, t is 28, right? Or negative 14 or negative 28. That herd might have been there for a while. We're just observing it today. Okay? How many people were there 28 years ago? How many whales were out there on the prairie 28? Well, not many. Okay? Well, then t equals 10 is going to be a vertical line through the coordinate 10 down here. And I'm going to put that between 0 and 14. Most of you understand that 10 is between 0 and 14. Well, everybody understands that. And hopefully you can kind of visualize that. How far are you from 14? You're only 4 units from 14. How far are you from 0? You're 10 units from 0. So you're a lot closer to 14 than you are to 0, right? And use a little common sense and you locate this thing. You don't put it over here closer to 0. You put it to the right of halfway, because halfway is easy to calculate. That would be t equals 7, right? You can even say, okay, t equals 7 about here. So t equals 10. I probably should have had it even a little further to the right. So I don't deserve the fact that my estimate came out pretty close. You know, it's deficiencies of the graph made up for the deficiency of where I put the t equals 10, and I happened to get a good estimate. But that was just an accident. Okay. Well, t equals 10. So what's y when t equals 10? Well, this curve represents this function. So we look at where the curve intersects the t equals 10 line, and then we draw a horizontal line to estimate what y is. The horizontal line is between 60 and 140. Okay? Sorry, it's between 60 and 120. So, you know, here's, maybe I ought to, I didn't want to get things too crowded over here, so I labeled 120 over here, but I guess we kind of need to see it. We have 60s here, 120s here. This is closer to 120 than it is to 60. So I'd say y equals 90, maybe 100 here. So just to use round numbers, I've said 100. Could have said 90 just about as well. No, I couldn't have said 90. 90 would be halfway. So yeah, 100 kind of, we're going to do it to the nearest 10. That's what we're compelled to do. Okay. So we're saying that, okay, I think y equals about 100 when t equals 10. Now, can I check that? Well, my estimate was y equals 100. If I plug 100 in for t, we get 98. So that means I lucked out and got pretty close. Now, some of the estimates we got in class, you know, people estimated 80. They put their line a little bit lower than I did. And they checked it out by putting t equals 10 into the functions. Okay, and they got y equals 60 times 1.05 to the t, where t equals 10, so use a calculator. They got 98. Okay, well, that is what it is. And that is what we get here. So we just calculated that. Now up here, I say, if we use function notation, y equals f of t equals 60 times 1.05 to the t, then at t equals 10, well, y is going to be, if t is 10, you're going to replace t by 10. So you're going to have f of 10. And of course, when you replace this t by 10, you have to replace this t by 10. And I don't really have room to write that very well, but I'll write it kind of small. It's going to be 60 times 1.05 to the 10th. Might be a little hard to read. You know, we were under duress when I did this because the computer was about to reboot. And when we plug that into a calculator, we get 98. Okay. Now, next question was, when is the value of 140? Okay. Now remember, one of the first things we did in the course was we learned to estimate the value of y given x, the value of x given y. Okay, so I'm spending a lot of time on something that everybody should really be in pretty good shape with. But there are people that aren't here, that want to be here, and hopefully will be here next week. And want to be complete in the video. So again, what's the value? When is the y value 140? Well, y equals 140 is just a horizontal line on the graph. It intersects the graph here. And now we can draw a vertical line to find out what T is, or to estimate what T is, and we get an estimate of T equals 18. Okay, now we didn't have time. Yeah, actually we did. Okay, so we estimate then that y equals, first we sketch the line y equals 140, and we estimate T equals 18. So that y equals 60 times 1.05 to the 18th. Now I estimated that'd be between 140 and 150, and I chose to round it to 150. It turns out it's 144 points, so it rounds off to 140. But 18 is pretty close to the correct solution. Okay. Now we want to talk about how to actually solve the equation. Okay. If y is 140, that means 60 times 1.05 to the t is 140 because y is 60 times 1.05 to the t. How do we solve this equation? So I'm going to give you a method, and then I'll explain why the method works. Okay. So I got this far to solve before the computer gods obliterated my next statement. Okay, well, to solve the equation, first of all, we do 60 times 1.05 to the t divided by 60 equals 140 divided by 60. Well, this gives us 1.05 to the t equals, well, going to be 7/3. So let's keep that in form 7/3. Okay, everybody understand how that comes about? That's very simple. Now, why do we do that? It's because we have the following rule. And from today forward for the rest of your life, remember this. Okay. Start by writing a better V. I'll blend the chalk with B to the A equals C. Now, is this in the form B to the A equals C? Okay. It is. What's the value of B? So we have a rule for what you can do to solve B to the A equals C. Because we want to solve for what? We want to solve for T, right? You don't have any algebra that allows you to get to a variable that's in an exponent, except you will in 2 minutes. Okay? Now, B to the A equals C is equivalent to, and I write the equivalent to symbol like this. It's not an equal sign. It's an arrow that goes both ways with like a double shaft. Okay? That sign means equivalent to. A equals log base B of C. Now, what in the world is this log thing, and what's log base B? Well, you have a log button on your calculator. I won't explain yet what the log is, but we will very shortly. Okay? It's a button. Right now, you can treat it as a button on your calculator. Now, we want to understand more about logs than that. But as far as solving equations, that's it. You have this equivalence. So how would I rewrite this in this form? A is T, B is 1.05, C is 7/3, right? So rewrite the equation. Let me just see what you do. Okay, well, here, this is the form. This form here, everybody sees that, but I want to write it out completely for anybody that's watching or will be watching. Okay. So I can write the same thing using the same values, A, B, and C, but I can write it in this form. And this form tells me T equals log base 1.05 of 7/3. This is the equivalent form. With the same values of A, B, and T. Okay? Now, how are you going to then evaluate this? You can evaluate this with your calculator. But you need one more rule. Didn't have room to write it out because I unwisely put this here. But log base B of C is log base C, is log of C divided by log of B. And you have a log button on your calculator. Okay. So using this rule, which is very simple, but you got to remember. It's the log of 7/3 over the log of 1.05. It's always the log of this divided by the log of this. Okay. And I got something wrong. No. Okay. An alternative form is natural log of C divided by natural log of B. On your calculator, you have a log button, and probably on the same key, you have a natural log button. It says LN, log natural. It doesn't matter which one you use. You're going to get the same result, and you ought to check that out. Okay, so let's see what the actual result ought to be. It should be just a little less than 18. I would say 17.7 or something like that. Punch it into your calculator. Log of 7/3 divided by log of 1.05. Okay, and we get something, I think it rounds off to 17.4, 17.36 something, is that right? Yes. So we'll round it off to 17.4. Okay, what's this do? This tells us what the graph would have told us if our graph had been completely accurate. Okay? There's no point in making the graph as completely accurate as we can, but it's always a good idea especially since I'm probably gonna ask you to do it on a test, and to construct the graph and make your estimates. Now you can fudge your estimates, and if you tell me the estimate here is t equals 17.36, I'm gonna say, ah, you fudging. Okay, I know you're fudging. But at least you know where it is and you got it in about the right place. So I'm gonna take a point off because I know you're fudging. But that's just mainly to hassle you a little bit because I know you know what you're doing, okay? Now, don't fudge your estimates, make honest estimates so you can get used to the idea of uncertainties and errors. That's really important. So, and that's pretty quick to solve it. That's an easy equation to solve once you have these rules, isn't it? Okay. Okay, so notice I made an estimate that y equals 100 when t is 10. Okay. And that was pretty close because y equals 98 when t equals 10. Okay, but let's just for practice. Solve f of t equals 100.
Did you get them mixed up?
I'm sorry.
Did you get them mixed up? I heard it say in progress instead of recording stopped.
Say once more.
I heard it say recording in progress instead of recording stopped.
Oh, I said that so well. I'm gonna go back and say what I said, but go ahead.
Yep.
Okay, now unfortunately, I might not have been recording what I thought I was. Which means who knows how. But again, we're trying to solve to see when this really is 140. And we previously said that that should be around the time t equals 18. If we plug t equals 18 in here, we get, well, I estimated it'd be between 140 and 150, and actually it's a little closer to 140. I think it's 144 point something. Okay, but at t equals 18, we're pretty close to 140. But let's find out what it really is 140. So what we have is, here's an equation. Okay. We divide both sides of the equation by 60, and we get 1.05 to the t equals 7/3. Now that's straightforward. Everybody can do that. Why did I do this? I did this because I have this rule up here. Very important rule. And I just put my line through my B, but I think you can read what it says. B to the A equals C is equivalent to, and there's the sign for equivalent to, like a double shaft on a double arrow. It's equivalent to A equals log base B of C. Okay. Now, using that, everybody did quite well. Everybody identified, okay, this is in this form with B equal to 1.05, A equal to T, and C equal to 7/3. So if we write the equivalent form is A equals log base B of T. Again, everybody identified it quickly that B was 1.05, A is T, C is 7.3. So we put the 1.05 here, we put the T here, we put the 7/3 here, and this equation then is equivalent to this one. And this one is really easy to solve. If you know the rule that log base B of C is log C over log B. Or natural log of C over natural log of B. Now, on your calculator, you might even have a log base B function. Okay, I recommend you don't use it because you're not going to have it when you take a test. You have a calculator to do logs, but it's not going to do log base B. I don't think it has a percent button in it, which is the main reason nobody understands percents anymore. Okay? You have to know a little bit of mathematics before you can use a calculator as anything but an absurd crutch. Okay, so NFT is this, and you just plug that into your calculator. Everybody did and got 17.36. Okay, roughly, and I rounded that to 17.4. Yeah. So there it is. Now we'll ask people to solve f of t equals 100. Okay, now I intentionally threw a little curve at you here. How do you solve f of t is 100? Well, f of t is still 60 times 1.05 to the t, isn't it? Okay. And here's your f of t function. I didn't use f of t here, but I did up here. And we used the expression for f of t to solve the original equation. So the expression for f of t is t times 1.05 to the t equals 100. You divide both sides by 60. And I'm just going to put a couple of dots here to indicate that if we divide by 60, we get 1.05 to the t equals 5/3. Now I skipped the step here. You shouldn't skip it. Okay. So that B is 1.05. A is t. C is 5/3. So t equals log to the base 1.05 of 5/3, which equals what? Log of 5/3 divided by log of 1.05. Okay, so what do we get from that? Okay, and we do that. Somebody got 10.47, which is completely consistent with what we see here. Okay. My estimate for y equals 100. Well, what did I estimate to get y equals 100? I estimated y when t is 10. So here's my t equals 10, and here's my y equals 100. Now, what this really, if this was completely accurate, this line would be about y equals 97.7. It'd be a little bit lower. Okay. It wouldn't be at, make sure we can see all this. Yeah. It wouldn't be at 100. The line would be a little bit lower. So that to get 100, we'd have to move a little further to the right. Okay. This point would be a little bit lower and the curve would have to move just a little further to the right to get up to the curve. Now, you want to think about that. You want to be able to see that because it helps you think about how these things work, how they change, and so. Okay. So what we got is a little bit to the right of 10. We got 10.47. Okay. And you're not going to estimate these things to four significant figures like this. All right. Okay, so that's actually pretty easy when you get used to it, isn't it? It's not bad at all. Okay, I'm asking everybody to sketch a rational function that has these x-intercepts, a vertical asymptote at x equals 2, and y goes to infinity as x goes to infinity. Y goes to negative infinity as x goes to negative infinity. Okay, now last time I gave you the equation of a function and asked you to construct the graph. In your homework, asked you to do some of that. Okay, but the homework also would show you graphs and say, what's the rational function here? Well, if you understand what we did in class and understand what open math tells you, you have a good shot at doing that, but it's not a simple thing. Okay, so let's just see what the graph might look like. We've got our x and y axes. And I'm going to just draw the line where x equals -7. Excuse me. In a line where I think x equals 5. And the x-intercepts will be, those two lines meet the x-axis. Now, we also have a vertical asymptote at x equals 2. Now, I draw that with a light solid line to indicate it's not just a construction line or something like that. It's a line that really has relevance to the graph. Okay. And let's see how that works. Well, we have a vertical asymptote here. Okay. Now, y goes to negative infinity as x goes to negative infinity. The graph can only go through the x-axis here and here. So what you have is a graph that comes up from way below, comes through here, and then kind of curves around to become asymptotic to this line. Pretty much the way the 1/x function, reciprocal function, would have an asymptote to the y-axis. Okay. And then question is, do you come down from the asymptote here and go through this point? Or do you come down here and just touch this point and turn around? Well, you can't come down here and go through this point because then you can't get back up so that y would go to infinity as x goes to infinity. So you know as a graph doesn't go through here. Okay? It can't go below the x-axis, but it could come down and just touch here and go up. And I didn't say enough to tell you whether that's the case or not. But for other reasons, we might as well just assume it acts like the 1/x function, the reciprocal function, at this asymptote. Now, the reciprocal function, would look like this, but of course, if you reflect the reciprocal function through the x-axis, which you just Now to multiplying it by a negative number, it flips around and looks like this. And that's kind of what happens here, isn't it? Okay, so it's like you've got a reciprocal function here. Could be a reciprocal cube function or, but I haven't been that specific. Okay, well, let's say that's it. Okay, now what's the equation of this function? So the equation could be y equals x minus 5 times x plus 7 in the numerator. Because if x equals 5, that's going to give you 0. And if x equals -7, that's going to give you 0. No matter what the denominator is, unless the denominator has an x minus 5 or an x plus 7 in it. And to get the vertical asymptote at x equals 2, your denominator, and you're going to need to understand what we did last time to get this. Your denominator has got to be x minus 2. Okay? So if you follow the procedures we did last time with this function, you're going to get a graph that looks like this. However, it could also be a multiple of this. So I'm going to say it's some multiple. I'm going to say it's a times this. Okay. And what's a? You don't have enough information to determine a. But I'm going to give you some information. I'm going to let you tell me. Here's your y-intercept. What's y equal to at this point? You give me any number you want. Okay, so first number I heard, I heard 5 and then I heard 2 just after 5, but I'm gonna have to go with 5. I could go with 52. That would be okay too, but yeah, I said the first number. I don't want to deprive anybody of the reward. Okay, so y equals 5. All right. Well, now y-intercept is at 0, 5. Then we have a number we can put in for x, and we have a number we can put in for y. Well, the x is going to be 0. That's the x coordinate. And the y coordinate is going to be 5. You get 0 minus 5, 0 plus 7 over 0 minus 2. So that 5 equals a multiplied by negative 35 over negative 2 is 17.5. Now it just so happens that 5 over 17.5, I can multiply the numerator and denominator both by 2 and get 10 over 35. So we get a perfectly good fraction. We could also just get a decimal. That's okay, but I like fractions when we can use them. Now, if this was 17.382, there's no neat way to get a reasonable fraction, and we would then just punch it into the calculator. But this is approximately equal to 0.28, maybe 29. Okay. Somewhere between 0.28 and 0.29. So now y equals 10 over 35. times x minus 5 times x plus 7 over x minus 2. Make sense? That's pretty easy. Now, in the open math homework, you're given a grid and stuff like that. You have to estimate your y-intercept. Or if you don't have a y-intercept, just estimate the coordinates at any point. Okay? Preferably a point where a couple of grid lines cross, because you're going to get a solution closer to the one open math thinks it wants. Okay? That makes sense? So if you understand what we did last time, why does this graph look like this? Okay. Then you can look at a graph, estimate its intercepts, and work backwards and find out what all the numbers ought to be. Okay. Now, there's another thing that's a little trickier, and I'm going to talk about that. But if you do this much, you're doing okay. All right. So if you didn't get it all on your homework, go to the late assignments page. Okay, you know where that is, don't you? Yeah. And work it out. And work out some of those problems, because you know, nobody got all the homework right. I didn't really show you how to do this. So if you do that, you know, for next class, yeah, I'll transfer your grade over, give you credit for what you've done since then. Okay. Now, let's say there's a little more to it. From what we did last time, I've got this graph doing this and doing this. Okay. Really, you would have a slant asymptote. You'd multiply this out, do a long division, and get your slant asymptote. Okay, and this doesn't have a slant asymptote. So now, if you saw that when you were given this information, and if you really understand this, you might see it, and did that on a test, I'll give you a couple extra points for recognizing it. Okay? For recognizing that, well, wait, this function has a slant asymptote, so the graph really should look more like no, I'm not sure what the slant asymptote ought to be, but let's just say it's like this. Okay, so it would come up from the slant asymptote to here, go through here and come up. And then it would come up through here and approach the slant asymptote. We talked about slant asymptotes last time. It probably wouldn't have this shape here, but you'd have to use calculus techniques to really understand that. So I wouldn't worry about that at all in this course. However, you want to do really, really well on this stuff. You have to have, you may maybe have this condition. Well, in that case, your intercepts would all be the same as over here. Point -70 here. 0.50 here. And a vertical asymptote of x equals 2. But it's got to go up here, and it's got to go up here. Now, if it's going up here and here, it can't have a slant asymptote. There's a slant asymptote, it's always going to go down on one side and up on the other. Worth thinking about. So let's go ahead and put our y-intercept here, and we'll call that 50 or 0.5. So how are we going to do that? Well, got to have this point, but if we come down from up here and go through this point, we can't get back up to this. Because you can't go through the x-axis unless you're at one of the zeros. So what's going to happen is you're going to have to come down here like this. And you got to flatten out. And you get down to this point, kind of like a parabola. And then you can come back up through here. I didn't do that very well. I did that so badly that I want to try it again. I think I can join up with my line there. But I just completely missed this because let's see around my hand. Let's see if I can do this a little better. That's a little better. Okay, so we just touch the x-axis here and go around. And then down here, well, we come on up through here. Maybe flatten out here a little bit and then go on. So that would be a reasonable graph. Now, what would the function be? I'll use A for my constant out in front, but we don't know yet. Okay, I could write this, but I know that this has this shape or this shape. Okay, it doesn't go through this point. This graph doesn't go through the 0 at -70. It actually acts kind of like a parabola or kind of like your toolkit squaring function. Okay, it just does this. And it's a little distorted, but it still has the same kind of behavior. And that tells us that we probably ought to have a square in this. Okay. And that way, when we're close to this point, the thing has kind of a parabolic shape. Now, the parabola kind of gets distorted because we're going all toward this asymptote and everything. But there is a reasonable equation. Didn't leave myself room between the word equation and the exponent that I should have thought about writing. Now, I know I was going to write the exponent, but I didn't anticipate it on the board. So let's just give ourselves a little room. Here's the equation. Now that equation will have this characteristic. Okay. At x equals 2, this is just like a horizontally shifted reciprocal function, shifted over so that the y-axis is over here at x equals 2. The other thing we know then is that y equals 5 when x equals 0. So 5 equals a multiplied by 0 plus 7 squared times 0 minus 5 over 0 minus 2. So 5 equals a times, well, that's 49. And 49 times 5 is 245. And divided by 2 is 245 over 2. So A is 10 over 245, which reduces down to 2 over 49, which is a little easier to understand. There we have it. Okay. That's worth understanding. If you understand that, then you understand most of what you need to understand quite well. Okay? If you just understand what we did in the previous example, you're okay. Okay, if you understand everything is of that nature, you know, that's kind of consistent with making a C, maybe even a B. But understanding all this is consistent with A work. Okay? And I think we're capable of making A's. All right.